Hi Jeffrey, how are you?
Oh, Uh, I'm doing all right. How are you?
Okay, okay. I'm fine. I think that everything is good.
That's nice.
So, what are we going to see today in class?
Um, yeah, so I guess we'll mostly be like wrapping up the central limit theorem, and then we'll start talking about a few new concepts such as modes of convergence, which I guess I promised like a little bit last time. Um,
Hmm.
and so we'll start with like statistical models and things like parameter estimation and confidence intervals if we have time.
Okay. What do you think about this course? Is it true that it escalates really fast and at the end is really complicated?
Can you repeat that? I think there's like some background noise.
Mhm.
Or sorry, can you repeat the question?
Yeah, okay, okay. Uh, let me ask you something. Is there a lot of noise here? Because
Yeah, I
I
think
think
there's
that.
quite a bit of background noise.
Okay, okay. So, as soon as the class start, I will turn off my mic, so I don't bother the class. So what I was asking is that is it true that the class escalates, the difficulty of the class escalates really fast, and by the end of the class is really complicated?
Yeah, I think at first, or like at first, I think it was probably seem like fairly quick because at least the first part, I think we like rush through like a review of probability and like start going over some like new concepts fairly quickly. Then I think in my opinion, like the difficulty like starts to lower a little bit towards the middle, but I think it begins to like pick up towards the end again.
Okay, okay, I get it, I get it. Well, I'm going to turn off my mic, so I don't annoy the class with the noise, but I will be here.
Right.
Hi, Jeffrey.
Hello.
How are you?
Pretty good. How about you?
Good too. It's colder here, but good.
Yeah.
Thanks.
Hi, good night, everyone.
Good evening, everyone. Yeah, I guess we'll give it a few more minutes for people to come to this Zoom meeting. Yeah, hopefully everyone's doing well tonight.
Hi, Jeffrey. Nice to meet you.
Nice to meet you, Alfonso.
Hi guys. Hello, Karin.
Ring.
Hello. Hi, guys.
Welcome, everyone. Yeah, I'm happy to see you turning on your cameras. So let's start. Today is the first time that we propose to have both of the generations together. We thought maybe this would be a good chance for you to talk to each other and to work on problems together. And to have maybe a bit of a competition with each other. I'm just kidding. So I would like to introduce Jeffrey, who is your recitation instructor. And then maybe he would think about how to start. Probably we might start with a breakout room for you to just mingle a bit and chat a bit, and then we'll start for real. So Jeffrey is a second-year undergraduate at MIT, currently majoring in mathematics. Some of you knew him from last week already. His main academic interest is combinatorics, theoretical computer science, and probability, with slight emphasis on optimization. Jeffrey was the TA for this course on campus last fall, and he had been tremendous help for the course. So, okay, so I'll let Jeffrey take it away.
Yeah, thank you, Corinne, for the intro. Yeah, so as you guys may have noticed, I guess we have both of the core hosts together for this time. So I think it would be nice if we started with breakout rooms first, just so both cohorts can mingle with each other. I'll be opening around 4 breakout rooms or so, just so you guys are able to mingle with each other. Feel free to use the help button or message me if you want to switch breakout rooms at any time. But I guess this will kind of be our introductory phase for this recitation. And yeah, with that, I guess I'll open the breakout rooms now. You guys can have around 5 to 10 minutes or so. Feel free to introduce yourselves to each other and tell each other anything you want to share, such as what you do or what you hope to get out of this course or anything like that. Yeah, and with that, I guess I'll open the breakout rooms now.
Yay, they all joined.
Oh.
Yeah, thank you for arranging this, Ellie.
Oh, you're welcome. Some of them are really like I always have problems to pronounce this word. Curious, like
Curious?
yes, like to see what's going to happen. Oh, we have Carlos and Manuel.
Okay, I'll let you do it.
Yeah. To those who just joined, I guess we're currently doing intros in breakout rooms. So I'll assign you guys to breakout rooms, and yeah, feel free to introduce yourselves to the other people in the breakout room.
Coloque sus manos atrás del asiento. ¿Qué? Hágalo.
So I'll be a fly on the wall. And Jeffrey, I would suggest that you encourage them to turn on the videos when they come back so that they see everyone. So, okay, I'll be around.
Okay, thank you, Karin.
Yeah, thank you, Ali. Ale? We are thinking, so Jeffrey and I are thinking of, today asking you for help for something, which is we would like to ask, whenever a student answer or comment on something, that we will ask them whether they are from generation 2 or 3. And then if you can keep track of the points for generation 2 and 3, and we will see at the end which group participated more, or
Okay.
or maybe we can have some sort of fun things for them next time, or so
Okay.
would you mind keeping track for us?
Yes, no worries, I will.
But I think Jeffrey, you'll have to say the rules of the game to everyone.
Yeah, so so as you notice, there's definitely a lot of people this time. So I would definitely encourage all of you guys to participate. I think if you can try to turn on your video, it will certainly help me to see if anything seems confusing based on your facial expression or any expressions that you make, if you can. But also, I think for this time, we'll try a special thing where every time I guess a learner offers like a comment or an answer to one of like my questions, or I guess also maybe ask a question as well. Feel free to also say which generation you're from, cohort 2 or 3, and we'll kind of like keep track of which cohort participates the most. Just so I guess like you guys can have like brownie points at the end or something. Yeah, does that sound good?
Yes.
Cool. Yeah, so let's get started with this presentation then. So this is kind of the outline of this week's presentation. So building off of what we started from last time, we'll kind of wrap up our discussion of the central limit theorem. And from that, we'll build up our discussion of the modes of convergence. This came up last time with the law of large numbers, and when I briefly discussed the central limit theorem, we'll discuss each mode of convergence in more detail, or at least the main modes of convergence that generally appear in statistics. And then after that, we'll move on to some new topics, such as statistical models. Technically, this is not all that new based on what we started with last time, but this is more of a way to like formalize what we were doing last time.
La madre.
Sorry, what was that?
Yo. Ah,
David,
hice popó de cusi.
David,
Sí,
Joel,
yo he pisado en el
Um,
baño. Quería orinar.
David, Joel,
Creo que
David, David.
yeah.
Ah, su madre.
I guess I'll mute David for now. Sorry about that. Yeah, so after discussing statistical models, we'll move on to parameter estimation and confidence intervals if we have time. Yeah, so that's going to be our main point of discussion for this time. And so actually, we'll first start with a warm-up that's not on the recitation sheet, but feel free to copy it down. So this is pretty similar to what we kind of discussed last time. So suppose we're considering some statistical experiment where we have a fair octahedral die or an 8-sided die. And each of the faces are numbered with the integers from 1 to 8. Oops, sorry. And so suppose we roll this die once, exactly once, and we denote the result of this rolling as x1. So x1 is and so from this, we want to ask, or our first question is, what is the sample space of the xi? What values can x1 take on?
Natural numbers from 1 to 8.
Yeah. Sorry, who is that?
Okay, I am Alfonso from the cohort 3.
All right. Yeah. So as Alfonso noted, the values that x1 can take on, or in other words, the sample space, is the set of integers from 1 to 8. 1, 2, 3, so on until 8. And this kind of makes sense because each of the faces are numbered from the integers from 1 to 8, and each roll of the die will yield one of these numbers. And so I guess the reasonable follow-up question is, how might we model x1 as a random variable? In other words, what distribution does it follow? Yeah, so often I'll abbreviate r.v as for random variable, if people aren't like too familiar with this.
A uniform distribution.
Right. Sorry, who is that?
Hi, I am Sebastian from Generation 2.
Right. Yeah, so as Sebastian noted, we might model x1 as a uniform random variable, I believe. Yeah. Distribution. But more specifically, because we're dealing with discrete values, we would call this a discrete uniform.
Is a discrete uniform with size h? I don't know how to say.
Yeah, so we would call this a discrete uniform random variable. And this would be over the set of integers 1 through 8. Right. So does this make sense to everyone? What we're like kind of doing here? Cool. I see a few thumbs up. Yeah, so this actually will be related to what we'll talk about a bit later with statistical models. But yeah, just try to like keep in the back of your mind what your thought process was when going through some of these questions, because these questions will kind of be relevant later on. But first, let's start by backing up a little bit and talking a bit more about the central limit theorem. Right. So recall our like kind of setup from last time. So we had x1, x2, xn as IID uniform or IID random variables. X1. So recall that IID stands for independent and identically distributed, which means that they're all independent of each other and they follow the same underlying distribution. Yeah, and furthermore, the expected value of each of the xi's is 1 or is mu. So expected value of xi is mu. And we also talked about the variance of the random variables. and suppose the variance is sigma squared. Then we had some expression that I'll kind of just like leave as a big box. And we said that this kind of expression in terms, oh, sorry. There's one other thing that I forgot to define. The last thing that we want to define is this sample mean, bar xn. In other words, we'll define it as the average of the xi's. Right, so then we had some expression where this expression is in terms of bar xn, n, mu, and sigma squared. Sigma squared. And this expression converges to a normal distribution, 0, 1. And so, yeah, the central limit theorem, I think, is one of the most important theorems in statistics. So before I tell you what the expression is in terms of x bar xn and mu and sigma squared, let's try to kind of build up the intuition behind what the expression should look like. So I believe this should be the first exercise in your recitation worksheet or your recitation sheet, but I'll also write it down here as well. So the first question that we might want to ask is, what is the mean of bar xn? So actually, before anyone answers, we'll kind of work through this in breakout rooms a little bit, just so people can discuss amongst each other what possible or what the answers might look like before reconvening and discussing the answers as a group. So the first question is, what is the mean of bar xn? The second question is, what is the variance of bar xn? And the third question is, suppose that we're given that xn can be approximated using a normal distribution. This is not particularly an obvious statement. And I think it requires quite a bit of work that we'll kind of just take as a given for now. We won't necessarily prove the statement of the central limit theorem. There are proofs online if you do want to look through this, but going through the proof will take quite a bit of time. But suppose that we're given that xn can be approximated using a normal distribution. In this case, how would we write the distribution that xn follows? So xn can be approximated using a normal, say, a comma b. Then what are a and b? And finally, after that, how might we transform bar xn to get the standard normal distribution? So here by transform, I mean kind of scaling all of the values by some constant c, or shifting all of the values by some constant c, or other things like that. And so we want to be able to get from a normal distribution with mean a and variance be to a standard normal distribution? Cool. Does everyone get what I'm trying to look for here? Cool. So I'll break you guys out into breakout rooms now. I'll actually be recreating the rooms so that they're a little bit smaller. So give me a sec. Yeah, while I'm doing so, feel free to think a little bit about this problem or this exercise. All right. Cool. So I'll open breakout rooms now. Feel free to discuss these questions among yourselves and then try to like come to a mutual understanding, and then we'll regroup in about 5 minutes or so or 5 to 10 minutes or so to go over these exercises. All right, enjoy.
Jeffrey. Jeffrey. Karim.
Yes.
I'm sorry, some students are asking if we can give them permission to share the screen in the breakout rooms. I think they cannot share the screen.
Yeah, we need to have Jeffrey back to have that.
Oh.
I'm not sure if we can do that actually. They should be able to, right?
Yeah.
Because I'm
I
not host.
think-
Um,
Oh yeah,
Yeah,
I
what do you
think he maybe joined the other sessions as a host.
yeah, I think so. Yeah.
I
Yeah,
will
do-
tell wait.
Yeah.
Maybe he will arrive before.
Yeah, but I even don't know whether we can change the settings right now. But we'll ask him.
Okay. Thanks.
Thanks.
Oh. I didn't change the setting. Let's see. Okay. Um, so I guess like I went to the share screen options, the advanced sharing options, and I clicked on all participants. So yeah, I guess I'll just like have to check whether or not this works when I guess we reassign breakout rooms later. Yeah, sorry
Yes,
about
I
that.
think yeah, don't worry. I think in the next breakout rooms will work. Yes,
Yeah.
that's okay. Thank you.
All right. Welcome back, everyone. So hopefully you got a better idea of maybe what some of the answers to these are and how we might build up the intuition behind the central limit theorem, or at least the expression that I boxed for now and left blank. So let's go through these exercises together. So I guess first off, what is the mean of bar xn? Yeah, feel free to just.
The mean is mu, and the
um,
variance is sigma square n divided on n.
Yeah, so I think some people also said it in the chat as well. But yeah, so the first off, the mean of bar xn is mu, because the idea is that we apply linearity of expectation to the xi's so that the expected value of the sum of the xi's is n times mu, and then we divide that by n because we defined bar xn as 1 over n times the sum of the xi's. Yeah, and as Diego also mentioned, actually, Diego, do you also want to say which cohort you're from?
3, the number 3.
Okay.
Jeffrey, I have a paper, and if you want, I can share us. Maybe. No.
Yeah, I guess feel free to type your answers in chat, maybe. Or do you want to like show your work?
I'm sorry.
Or yeah. Do you want to like show your work, or do you want to just like go through the answers? Yeah, actually, yeah, I think someone essentially like posted some of their work in the chat. So basically, I think Diego also mentioned that the variance of the bar xn is sigma squared over n. Here we're using the fact that the xi's are independent. So if we want to look at the variance of the sum of the xi's, we simply add their variance, or we add their variances together. So because each of the individual variances is sigma squared, their sum would be n times sigma squared. And then whenever we divide a random variable by some constant, in this case n, we would divide the variance by that constant squared. So we end up dividing n times sigma squared by n squared. And so that's how we get sigma squared over n. And then building off of that, if we were to approximate xn or bar xn using a normal distribution, A would end up being the mean, which is mu. So, and B would be the variance, which we saw was sigma squared over n. So we could further write this as normal mu sigma squared over n. And yeah, as Lauren said in the chat, Lauren, feel free to also type your cohort number in the chat. Yeah, and also for anyone who wants to answer in the chat, feel free to also just like type your cohort number in the chat. But how we might transform this is first we move the distribution so that it's centered at 0. So in this case, we would subtract mu from bar xn. So we would get bar xn minus mu. And this would be distributed according to approximately a normal distribution with mean 0 and standard deviation or variance sigma squared over n. And then kind of following what we reasoned through with the variance of bar xn, we would divide by the square root of the variance, because in this case, whenever we divide a random variable by a constant, we end up dividing the variance by that constant squared. So in order to get this quantity down to 1, we would divide by sigma divided by root n. So we end up with sigma or root n over sigma times bar xn minus mu is approximately the standard normal distribution. Yeah, and so we can go back and fill this out as root n times bar xn minus mu over sigma. All right. Does anyone have any questions about any of these? Cool. So yeah, that's most of that. Hopefully that gives you some sense of how the central limit theorem works, kind of. Besides like taking into granted that the distribution of the sample mean will follow something that is approximately a normal distribution. This hopefully gives you an idea of where the quantity mu, sigma, and root n come into play. I guess technically it's sigma instead of sigma squared, but yeah. So I think one of the things that we probably want to pay attention to is what kind of convergence is at play here. And so, yeah, so this is what we call a convergence in distribution. So the idea here is that the probability distribution that you'll get is the same kind of on both sides, in the sense that if you look at how the bar xn's are distributed, the distribution seems to somewhat like converge to or be approximately the normal distribution. But yeah. It might not necessarily be the case that the values that both sides kind of take on are the same, but at least the kind of like probability distributions that underlie the random variables are the same. And so recall that we had two other types of convergences from last time, or possibly from some of the lecture videos that you might have watched. We also had convergence in probability and convergence almost surely. Both of these came with the law of large numbers. And so this is one of the things that we'll go over today, all three of these modes of convergence. Yeah, so whenever we're talking about convergence of random variables, we always have some sequence of random variables. So say, for example, like x1, x2, x3, so on until xn, so on. So in the case of the central limit theorem or the law of large numbers, we were considering the xn's to be the sample means, but these can be some other sequence of random variables that we're considering. And we'll also have some other random variable x that we're comparing this sequence to. Right. And so kind of thinking about it in terms of this framework, we can start from the weakest mode of convergence to the strongest mode of convergence. So the first mode that we'll talk about is convergence and distribution. And you'll often see this denoted with a right arrow with a D on top of it in parentheses. And so we say that x1, x2, so on until xn converges to x in distribution, which we can write like this. If capital F of xn of x approaches capital F of x of lowercase x as n goes to infinity. So yeah, so first, I guess I want to ask, is everyone familiar with this notation here? Does someone want to, yeah.
Is the CDF?
Yeah. Yeah, so this is denoted, we usually use capital F and a subscript of some capital letter, which is some random variable, to denote the CDF, or the cumulative density function, I think. And so kind of what this is saying is that if we also can think of this as the probability that the random variable x is at most x, or lowercase x, we can think of this as the probability distributions will end up being approximately the same, in the sense that like yeah, the kind of like the probability that for example, like xn is at most x will be approximately the probability that capital X is at most x. And in this case, like this is enough to like kind of show that like the cumulative density functions are roughly the same, and thus the underlying probability distributions are the same. Yeah. So the second mode of convergence that we'll look at is convergence in probability. Which we'll denote with capital P, sometimes with 2 bars above the arrow. And we say that the sequence xn converges in probability to capital X if for all epsilon greater than 0, the probability that xn minus x is greater than epsilon approaches 0 as n goes to infinity. So in other words, the probability that the xn's will deviate by more than some amount from x will approach 0, essentially. In that, essentially, like if you look at the probability in terms of, for example, like n, that xn minus x is greater than epsilon, this probability should go to 0 as n goes to infinity. And this is the type of convergence that we see in the weak law of large numbers. So for example, we say that, like, for example, the sample mean bar xn will converge in probability to the mu, in the sense that as n goes to infinity, the probability that the standard sample mean will deviate by more than like any epsilon from mu will approach 0. Yeah. And the third mode of convergence is a little bit trickier. It'll seem a little bit familiar, or it'll seem a bit similar to convergence in probability, but there is kind of a subtle difference going on here. So this is convergence almost surely. Which we'll denote with an AS on top of the arrow. And we say that xn converges almost surely to x if the probability of this statement xn approaches x as n goes to infinity equals 1. So what we're saying here is that xn will almost always end up converging to x, and the subset of events for which xn will not converge to x has total probability 0. Oh, sorry. I see there was a question in the chat. Which one were you referring to in terms of like, is this not the expectation?
I think is the first case. In the convergence in distribution is
No, I mean on the convergence in probability, professor. In the example of x converging in probability to mu is not the expectation of x converging in probability to mu.
So that's actually a different form of convergence. So there's actually a whole separate like other set of convergences called convergence in means that I'll go over briefly after, or I'll go over briefly after talking a little bit about convergence almost surely. But yeah, that's definitely a good point to bring up, because I think there was also a few exercises on edX that also kind of brought up some convergence in means. But yeah.
Okay, thank you.
Yeah. Yeah, so returning to convergence almost surely, the idea here is that basically you can guarantee that like xn will always converge to x, and unless you're in some like subset of events whose total probability the union of the probability of the union of the events is 0. And the term almost surely here comes from the fact that, you know, there might still be some events for which xn doesn't really converge to x, but these events have total probability 0 of happening. And it's kind of like the probability that, for example, like if you have a uniform random variable, y, the probability that you get that y is equal to 1 is 0. And so you can kind of like think of that as like kind of like an example of what we mean by like events that have probability 0 of happening. And similarly to convergence and probability, this type of convergence appears in the law of large numbers, where instead of saying that it converges in probability, it converges almost surely. Yeah. I generally think that this form of convergence almost surely, probably won't come up as often. I think it's also one of the most confusing modes of convergence to understand, especially like the difference between convergence and probability and convergence almost surely. But it's something that's good to know, I think. And then lastly, what was mentioned earlier, we also have this other notion of convergence, which I write as L to the N convergence. Which we denote with an L to the N. And so we say that xn convergence to x, or I guess this ln convergence happens if the expected value of the difference xn, oh yeah, actually I'm using the same variable twice, sorry. Let's use m instead. So this L to the M convergence will happen if the absolute value of the difference between xn minus x, raise that to the nth power, goes to 0 as n goes to infinity. And so if L equals 1, then we're just talking about the absolute value, the absolute value of the difference. If m is 2, then we're talking about the square of the absolute value of the difference, and so on. And this is kind of like where the expectation comes from. Yeah, I think this one, yeah, does someone have a question?
Yeah, and the m can't take any value from, I mean, numbers.
Yeah, so I believe at least m can be any positive integer. It wouldn't necessarily like make sense, I think, to say m is equal to 0 or something like that, but we can at least have m be any positive integer. There might be some notion that generalizes this to the set of real numbers, but I'm not too sure about this. But m can be any positive integer here. And I think maybe one of the most important thing, I think one of the important things that you might want to remember is that L to the M convergence implies convergence in probability.
So maybe could I ask to elaborate a little bit further in convergence in probability?
Yeah.
To deeply understand.
Sure. Oh, is there like anything in particular you wanted like elaborated on?
Maybe do some examples with something real.
Yeah. So, yeah. We'll definitely like. Let's see. See. Yeah, so I guess maybe one example for convergence in probability is, say you have the sequence of random variables, x1, x2, xn, which such that xi is distributed according to the Bernoulli random variable, or the Bernoulli distribution with parameter 1 over I. And so in this case, the xi would take value 0 with probability 1 minus 1 over I, and take the value 1 with probability 1 over I. And so in this case, we would say, you might notice that as n goes to infinity, the probability that each of the xi's will each of the xi's will be 1 approaches 0, while the probability that the xn takes the value 0 will approach 1. So we can say that xn converges in probability to 0. Yeah. So does that like kind of help a little, that example?
Anyway, I'm gonna check it later to really understand.
Yeah, no worries. I definitely understand that like these convergences seem a little like abstract, and especially like just looking at the definitions themselves. So what like kind of initial questions do people have about this? We'll definitely like go over like a few concept questions to like build our understanding of this, but are there like any initial questions that people have? Cool. So let's move on to the first concept question. Let's see. So we'll actually be, I'll actually like post a Google form for this. So try not to like give away the answer in the chat. Make sure that like everyone has a chance to think about this and answer on the Google form that I'll send out in a little bit. But yeah, so the first question is, suppose that we have some sequences of random variables, x1, x2, xn, and y1, y2, yn. And suppose x and y are random variables that satisfy xn converges in distribution to x, and yn converges in distribution to y. Is it always true that the sum of the sequences, in other words, like x1, x2, or x1 plus y1, x2 plus y2, xn plus yn, is it always true that this converges in distribution to x plus y?
No, because it's necessary that one of the two random variable is convert to a real number. There is a term I don't remember, but it is a random variable. Both is don't conversion in distribution.
That certainly seems like a compelling argument, but yeah, I'll actually post a Google form in the chat. Feel free to answer there. We'll try to like see what everyone in the class thinks. If there's like some split like 50-50 between yes and no, we'll break out into breakout rooms so that people have a chance to discuss amongst each other. But otherwise, we'll kind of go through this as a class. So we'll give it about 1.5 more minutes, and then I'll share the results. Okay, yeah, so just to, I guess, clarify the question in the chat, the xn's don't, or the sequences of random variables don't necessarily have to be IID. let's give it 15 more seconds and then I'll share the results. All right. Share. All right. Yeah, so it looks like at least a simple majority did think that the answer was no. And I think someone tried to like give an explanation, at least in the sense that like, you know, this at least like somewhere in the lecture notes, it said that like this doesn't necessarily hold or like adding two sequences of random variables doesn't preserve like convergence and distribution, but it does like conserve convergence and probability and almost surely. But I think an interesting thing to kind of ask is why is this like not the case? And does anyone have like an idea of like why this might not be the case? Let's see. Yeah, so
Okay, I thought in the case when the two variables are dependent.
yeah, so Alfonso, do you want to say which cohort you're from? Or
I'm from cohort 3. I already see. I already say.
yeah, okay. Yeah, so basically one of the things here is that it might be the case that the x ends and the y ends are somehow correlated, and somehow like adding these random variables together just like messes up the distribution that is like underlying these random variables. So an example of when this might happen is, for example, if each of the xi's, x1, x2, xn are all IID. So this is kind of like a counterexample of like when this is not the case. So for example, say like x1, x2, so on until xn is IID distributed according to a standard normal distribution. And so in this case, we would have that xn converges in distribution to the standard normal distribution, or yeah, or it converges in distribution to an x where x is a random variable that follows the standard normal distribution. However, let's kind of like incorporate some of this like correlation here. So what if we define y1 such that y1 is equal to minus x1? And similarly, y2 is minus x2, and so on until yn is minus xn. And so here in this case, we can first think about the sequence of random variables y1, y2, and so on until yn. What distributions do these random variables follow? Yeah, I see an answer in the chat. The idea here is that the y-ends will also follow a normal 0, 1 distribution. Yeah. Yeah, because the idea is that negating a normal random variable doesn't really change the underlying distribution, because the standard normal distribution is centered around 0. And so that means that each of the y-ends will also follow a standard normal distribution. And so in this case, we can also say that yn converges in distribution to this value of x as well. Or I guess we can also write this as like y, where y follows this distribution. And so now let's look at the sequence x1 plus y1, x2 plus y2, and so on. Because of the way that we defined it, x1 plus y1 will equal 0 because we defined y1 as the negation of x1. And similarly, x2 plus y2 is also 0. And so on until xn plus yn is 0. So that means that n plus yn will converge in distribution in probability almost surely to the random variable. I guess we can say z, where z is identically 0. Or I guess we can also write this as just converges in distribution to 0. However, if we look at what the sum x plus y is, if we're taking the sum of two normal random variables, then we end up with a distribution that's a normal distribution with this sum of the means and the sum of the variances. So in this case, x plus y follows a normal distribution with mean 0 and standard deviation 2. And in this case, this is not equal to the distribution, which takes on 0 with probability 1. So that means that we don't have this convergence here, that xn plus yn doesn't converge in distribution to x plus y. Yeah. So does anyone have any questions about this example? Cool. Yeah, so hopefully people will get the idea that we're kind of just like looking at, in this case, we're building an example off of what was said earlier about kind of like correlating the two sequences and to like build a counterexample to convergence in distribution when we sum these. Yeah, but as it turns out, we do have some results when we're like summing the sequences of random variables. So if instead we replace convergence in distribution with convergence in probability and convergence almost surely, we do actually have that if xn converges in probability or almost surely to x and yn converges in probability or almost surely to y, then we do have that xn plus yn converges in probability and almost surely to x plus y. And so hopefully this like kind of gives you a sense of why convergence in distribution might be the weakest form of convergence, because it's like fairly easy to like mess around with, whereas like convergence in probability and convergence almost surely kind of have these like more strict behaviors in some sense. And similarly, you can replace addition with multiplication. So we could have xn times yn converges in probability or almost surely to xy. And I think as someone mentioned earlier, we also could have, for example, if xn converges in distribution to x, but yn converges in probability to some constant c, then these kind of results will also hold, in the sense that xn plus yn will converge in distribution to x plus c, and xn yn will converge in distribution to c times x. and also division will end up holding. So xn over yn will converge in distribution to x over c. And so this actually has a name to it. This is known as Slutsky's theorem. And this is kind of one of the tools that we have whenever we're dealing with convergence in distribution. Because convergence in distribution can often be fairly easy to mess around with, as we saw earlier. There is another tool that I won't go over for the sake of time that we have when we're dealing with convergence in distribution that also works with convergence in probability and convergence almost surely, which is the continuous mapping theorem. But a high-level overview of this is if xn converges in if xn converges in any of the three modes to some random variable x, and we have a continuous function f, then applying f to each of the random variables xn, this sequence of random variables will converge in any of the three modes, or the three modes that correspond to what we were looking at beforehand, converges to f of x. So for example, if f of x is x squared, then for example, if xn converges in, say, distribution to x, then we could say that xn squared converges in distribution to x squared. Yeah, and so this is a key idea behind the second concept question, but we won't go over it for the sake of time. Yeah. Does anyone have any questions overall about these different modes of convergence? Hopefully this exercise kind of gave you maybe a better idea of how these different modes of convergence.
Jeffrey, I have one question. In the continuous mapping theorem, what type of conversion is about?
Right. So I guess going a bit more in detail to this. So this continuous mapping theorem will actually hold for all modes of convergence. But the mode of convergence that we get when we apply the function f will be the same mode as the mode that we had initially. So for example, modes. So for example, if xn converges in distribution to x, then that implies that f of xn converges in distribution to f of x. And then similarly, if we replace this with convergence in probability, then we would be able to get convergence in probability. And if we replace this with convergence almost surely, we would also have convergence almost surely. Does that help answer your question? All right. Are there any other questions before we wrap this up? All right. Yeah, so hopefully this kind of gives you a sense of the different modes of convergence. I think these will tend to pop up when we're looking at other tools that we have. I think convergence almost surely and the L to the N convergence won't pop up as much, but definitely we'll see a lot of convergence in distribution and convergence in probability. And it's just like kind of useful to like keep in mind what these types of convergence modes are trying to say. And so with that, let's move on to something, I guess, completely new. Not necessarily like completely new, but more, just like more of a more formal way of looking at this. And so we'll start looking at statistical models. Right, so we've actually already been talking about this quite a bit, kind of with our discussion from last time about, like modeling coin flips or other things. And with our warm-up as well, with like talking about what the like outcome space is and what like distribution that we're looking at. But here we're going to like kind of take a more formal look at this. And so suppose we're like considering a statistical experiment. And we have n samples that are x1, x2, xn, which we assume to be IID, distributed according to some common distribution P. In other words, we're drawing n samples from the same common distribution P independently and at random, I guess. Yeah, so that's our kind of like setup for what our statistical experiment is. And here we kind of define a statistical model to be an ordered pair. Where, so first, the first part of our ordered pair is this curly E or uppercase epsilon. This is what we call the sample space. And the second part of our statistical model is a set of probability distributions, which we'll denote as P theta, where theta is from some set T. And so kind of like labeling each of these parts, we have T is the parameter space. Theta is what we call a parameter. And P theta is the distribution corresponding to theta. Yeah, so I guess like as an example of this, if we were to kind of build off of our coin flips model from last time, so kind of recall that when we're talking about coin flips, we say that we have like a two-sided coin where the probability of landing heads is some unknown quantity P, but we know that like the set of probability distributions that we should be looking at is the set of Bernoulli probability distributions. And the sample space here, we modeled as 0 for heads and 1 for tails. So in this case, for coin flips, we could write this as the sample space is 0, 1, where 0 represents tails and 1 represents heads. And the set of probability distributions that we're looking at is the set of Bernoulli distributions. Bernoulli P, where P is some number between 0, 1, where you could include either 0 or 1. It doesn't particularly matter. Sometimes it might be more valid to leave out 0 or 1 depending on the experiment at hand. But either way, both of them are like valid statistical models. Yeah, so oftentimes we'll be dealing mostly with what's called parametric statistical models. Where essentially like our parameter space is finite dimensional. Or some subset of R to the D, where D is the dimension. There are other statistical models, such as non-parametric and semi-parametric statistical models, but we often won't be dealing with those in this class. And we often want our statistical models to be well specified, in the sense that there actually exists some parameter theta such that our initial distribution that we're pulling samples from is equal to P of theta. This is kind of like we're actually like looking at a set of probability distributions that is kind of like suitable for the problem at hand. So for example, it might not be really suitable to look at, say, the set of binomial distributions when we're looking at each individual coin flip, because the binomial distributions can take on more values than 0, 1, for example, or it can take on more than just 2 values. Cool. So yeah, so let's move to the first exercise, I guess. So the first one, which I'll put you guys in breakout rooms, is, let's start out like a little bit simple. Let's think about like how we might construct 1 or 2 parametric statistical models. So construct 1 to 2 . And when you're thinking about constructing these statistical models, I guess I should also specify that they're parametric. Yeah, when you're thinking about constructing these parametric or statistical models, try to think about which parts of your model represent the sample space, which parts represent your parameter space, what's your parameter, and what set of distributions you're looking at. And kind of as a bonus, think about what your statistical model would like represent in the real world. So for example, in the case of this statistical model, we would say that it might model like doing like coin flips in real life, for example. Yeah, so does everyone get the exercise? Cool. So I'll put you guys in breakout rooms for about 5 minutes or so. Try to come up with a group, a few statistical models, and try to think about like what they might represent and what the individual parts of each of the models are. And good luck. All right. Yeah, so now that everyone is back, did anyone come up with any good examples of statistical models? Feel free to like type them in chat or try to like explain each of the individual parts. Aris?
Hi, Jeffrey. In my group, we came up with a model to describe this group. So the second cohort and the third cohort. So we think that the values are between 21 and 37.
37.
Approximately, the distribution is a mixture of Gaussians. The cohort 2 has the first Gaussian, and the cohort 3 has another Gaussian. And the probability, but it's not the full Gaussian, it's between limits, between 21 and 37. Okay, and the probability is between 0 and 1.
Oh, sorry, I didn't catch that fully. Do you mind repeating again?
The last part or which part?
Okay, wait. So you said that the set of values is between 21 and 37, right?
Yes.
Okay,
Then it's a mixture of Gaussians,
right.
and the probability lies between 0 and 1. But it's not full Gaussians because it has bounds, no, according to the
Yeah.
age of a people.
Yeah, so yeah. Let's see, P between 0 and 1. Yeah, so this is definitely a very, I think, yeah. I think this is a good, this is probably a good place to mention that, yeah, I think, let's see. Yeah, so I think for now, I'll just like use probably more of this like notation for now, because like I think this ends up being like somewhat complicated, because one of the things that I guess this is something that I somewhat forgot to go over is that one of the things in statistical models is that you need to make sure that the probability distributions that you're looking at, the sample space of those, or the outcomes that you can get from those probability distributions is some subset of the sample space. So I think Aris mentioned a good point that like the values here would end up having to be bounded between 21 and 37, because or like you would have to specify that when you're specifying the set of probability distributions that you're looking at. Otherwise, the set of the mixture of Gaussians will end up taking on every single real number from -infinity to infinity. So yeah, Bernick?
Yes, Professor. I was thinking about maybe if we ask about to people if they have a specific illness and they have maybe have or not have this illness, and I think this can be modeled as a Bernoulli random variable.
Yeah. So yeah, I think this is probably pretty similar to the coin flips example, where we, instead of like saying, oh, 0 is heads or 0 is tails, 1 is heads, we instead say like 0 is not have and 1 is have, or something like that. Is that kind of like what you're going for?
Yeah.
Yeah. So I think the statistical model that you're looking at ends up like being the same as the coin flips statistical model. But I think Laren also mentioned in the chat where you can also actually further restrict, for example, your set of parameter values. So this is actually this looks roughly the same, except instead of saying that P is between 0 and 1, we can say that we can restrict P to be between 0.1 and 0.3. So this is also another valid statistical model.
Yeah. Yeah, the parameter P is restricted in the interval 0.1 and 0.3, which is perfectly valid because we know that the P is between 0 and 1.
Yeah, exactly. Yeah, so in some sense, you're just like taking a subset of the set of real numbers between 0 and 1. Yeah, so hopefully this kind of gives you a better idea of how to construct statistical models, or at least like how like statistical models look like. I think oftentimes when you're trying to look at like statistical problems, or when you have like statistical experiments, it's often a good idea to write these types of statistical models down, because it helps you like focus on, oh, what is exactly the sample space that we're looking at? Is it like, for example, the set of positive integers, or is it like the set of positive real numbers, or is it the set of all real numbers? And more specifically, like what probability distributions are we looking at? Are we looking at, say, like a binomial distribution? Are we looking at a Bernoulli distribution? Are we looking at Gaussian distribution, or like a mixture of Gaussians, for example? These are often like questions that you want to consider when you're creating a statistical model or writing down a statistical model for your experiment. Yeah, so I think maybe another thing that we want to keep in mind when we're writing down a statistical model is this idea of identifiability. And so I think one of the like maybe good ways to illustrate this is, so say we have this type of statistical model where, okay, so say our sample space is the set of real numbers, and we're looking at the set of normal distributions with mean 0 and variance theta squared. And theta is just some real number. So is there anything that stands out to anyone that seems a little strange here? So I'll maybe like point to two places where things might not be like that good. So the first is that theta ranges, if theta is just some real number. We have like no further restrictions other than theta is a real number. And the second one is that our variance is defined as theta squared. And yeah, actually, I guess maybe another thing to mention is that oftentimes when we're building statistical models, we want to have the goal of eventually finding the parameter at hand. So like, what about these like two things kind of makes it hard for us to find the parameter?
Maybe theta should be explicitly positive.
Yeah. Which cohort are you from?
Cohort 3.
Yeah. So Alessandro mentioned that maybe instead of having theta be just like over all real numbers, we want to like somehow restrict it. So and the idea here is that if we didn't, then say for example, we looked at like theta equals 1. In this case, we would be looking at the normal distribution with mean 0 and variance 1. However, if we looked at theta equals -1, then we would be looking at the normal distribution with mean 0 and variance -1 squared, which ends up being 1. And so here we see that we have like two different parameters that end up giving us the same distribution. And so that really makes it hard for us to find out whether or not, for example, like theta should be 1 or if theta is -1. And so oftentimes a good, at least in this case, a good fix would just to be, or would be to say that, oh, we restrict theta to be over the set of all positive real numbers or the set of all non-negative real numbers. But this kind of highlights a key point that we want to like keep in mind when we're creating a statistical model, which is this idea of identifiability. So we say that theta is identifiable, where theta is just theta is some generic parameter that we're talking about here. If and only if this holds. So if there's some other theta or theta prime such that the two the two distributions according to those two parameters or p theta is equal to p theta prime, then that means that theta prime has to equal theta. In other words, no two different parameters can produce the same distribution. Yeah. So does anyone have any questions about this concept of identifiability? Cool. So yeah, so I guess just as one final exercise before we call it a day, let's look at the first exercise in the identifiability section. So here, let's suppose we're considering the binomial statistical model. So where our sample space is the set of all non-negative integers and our set of probability distributions is binomial. Oops. Where n is in the set of natural numbers and Q is some real number between 0 and 1. I know I think I wrote in the recitation worksheet that this is a closed interval. That was actually kind of a mistake. This should be an open interval. Yeah. So let's consider this statistical model. So the first question is, what is or are the parameters? Yeah, so for this exercise, feel free to just like shout out the answer or any thoughts that you have on this question. Yeah. So as was noted in the chat a few times, the parameters here are n and q. So the second question is, what is the dimension of the parameter? Or what is, yeah. So in other words, like how many parameters are we dealing with here? Yeah. We're dealing with 2 parameters, so our dimension of the parameter space would be 2. And lastly, this one, yeah. Lastly, we want to know, is the parameter, or are the parameters identifiable? So in other words, is there some 2 settings of n and q that produce the same distribution, or is this not the case? This one might be a little tricky to explain, but feel free to like give whatever thoughts you have about this. So I guess I'll scroll up a little bit just so the definition of identifiability is there. I see a no in the chat. Let's see. Why do you think it's not identifiable? Yeah, feel free to just like give a kind of informal explanation. You don't need to be like too rigorous here. if you have the same proportion, not necessarily comes from the same n. So are you saying that like are you saying that like if there might be like two different settings of n that if you take the same value of q, you would get the same distribution? I see. Let's see. Yes.
I have an observation there. Is that a closed interval or an open interval?
Yeah, sorry, it should be an open interval. I know.
Yeah.
I think I said
because
like I
close it. Maybe if we have 10 or 5 trials and the probability is 0, then the result will be always the same, right?
Yeah, that's kind of why I had to change it at the end. Sorry. See, we could say if the Bernoulli is injective, then the collection of n random variables. Yeah, I think both of these seem like interesting approaches, I think, to the same problem. Yeah, I think essentially like let's see. Yeah, so I think in terms of like arguing that there are two different settings of n that, or yeah, two different settings of n such that there exists a value of q that makes the distributions equal. I'm actually like not too sure about this because if you think about it, I guess like if you have two different settings of n, then what values can the binomial each of the binomial distributions take on? Because say you had, for example, like binomial n q and binomial n prime q. In the former case, this one would take on the values 0, 1, 2, so on until n, with positive probability. However, this one would take on the values 0, 1, 2, n prime, with positive probability. So I think it would be like kind of hard to say that if you had two different values of n, then you could choose some like q such that both of these had the same probability distribution. Does that like kind of make sense? Yeah. I think as for the other point, I think that's, yeah, I think that's part of like, that definitely helps us understand that actually the parameters are identifiable. And so kind of like one way to tell is, suppose there were two different settings, like binomial nq and binomial n prime q prime, such that the two distributions end up being the same. Well, in order for the distributions to be the same, the expected value of the distribution has to be the same, or the expected value of a random variable following that distribution has to be the same. And similarly, the variance of the random variable that follows that distribution has to be the same. And so kind of like in this case, we notice that, for example, this binomial distribution has expected value equal to NQ, and this one has expected value equal to N prime Q prime. And similarly, the variance here, following the fact that a Bernoulli is the sum of, or sorry, the binomial random variable is a sum of n Bernoulli random variables. The variance here would be n times q times 1 minus q. And the variance here would be n prime q prime 1 minus q prime. And so in order for these to be equal, this means that 1 minus q has to equal 1 minus q prime by dividing out n times q and n prime times q prime from both sides, which tells us that both of the q values have to be the same, which in turn tells us that the n values have to be the same. Yeah. So this is like kind of an example of what types of steps you might run through when you're trying to think about whether or not a parameter is identifiable. If you think it's identifiable, then try to think about what happens if you have two different settings of the parameters and show that if they were to have the same distribution, then you can show somehow that their parameters have to be the same, either through arguing that, for example, their expected values are the same, or the variance has to be the same, which means that the underlying parameters have to be the same. And if you think that the parameter is not identifiable, then you might try to construct two different settings of the parameters such that the underlying distribution is the same. Yeah, so does anyone have any questions about this last example? All right. So yeah, so I guess it's 10 over or 10 past 10 here in Boston. So I guess we'll stop here. Yeah, so I'll post a Google form in the chat. This is mostly if you have any feedback, for example, on the pacing of the recitation, the difficulty of the material covered here, and any additional feedback that you have. Definitely fill this out. I would definitely appreciate whatever feedback you have. And yeah, other than that, I guess we can call it here. Have a good night, everyone.
Thank you, Jeffrey. Good night.
Thank you, Jeffrey.
Thank you,
Thank you, Jeffrey.
Thank you, Jeffrey.
Thank you, Jeffrey.
Have a good day. See ya.
Goodbye. See you.
Good night.
Thank you, Jeffrey. We won't talk tonight because I think you must be tired.
Yeah.
We'll see. It looks like cohort 3 is the win tonight. We'll see what to do with that.
Okay, thank you. I will